And it's just this famous, beautiful exposure of rocks that has an exceptional geological story behind it. Chris, welcome to PlanetGeo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. No, not sit in a row.
Yes.
Sit in a row.
Yeah.
No. Smudge
I remember
fingers.
that.
Smudge thumb.
Smudge.
Smudge thumb.
I do like that, and I like it when you get that processed cheese all caked up on your fingers, and then you just save it up, and then you lick it off. Yeah.
No, that's not what I'm talking about. It's mostly Dorito powder that you're licking off your thumbs.
Yeah, well, you call me smudge fingers. That's why.
And then you put your smudgy fingers all over the phone or all over your computer camera and get your image all smudgy. It drives me nuts. I can't record good video anymore.
Well, nobody needs good video of Chris. Okay, nobody needs
exactly
that.
Right. Prefer to have it smudgy. Hey, Chris, today.
Yeah.
This
listener
is
question time.
But here's a question for you. The White Cliffs of Dover, the geology of the White Cliffs of Dover. And we're going to talk about the geology of chalk in general here. But is this...
Does that sound exciting, Jesse? We're going to talk about the geology of chalk. When we first started thinking about this, we're like, that's an interesting question. Well, let's do it. And so I kind of have this idea. We did Petoskey stones, Now we're doing chalk. I want to do one on stromatolites also.
Oh yeah,
it's
okay,
all
definitely
related,
do that.
And so we'll have a little mini series on these microscopic organisms that were super important during their times. Yeah.
Is this, Chris, the first episode? It can't be the first, but I couldn't remember one that had the first episode on an international, outside the U.S. location specifically. That can't be right.
No, it's not. Okay. Nope.
We've done.
We did one on
the Hellgate, the Spartan.
We did that. The Spartan 300. But we also did one on. It was a mass wasting event that happened in the UK.
Yeah, you're right.
Do you remember that?
Right. Yep.
So
that's right. Yeah. It was a weird. Yeah, it was a weird soil creep phenomenon. Yeah, that's right. Okay, we've done a couple. This is our second or maybe third on UK geology. But this, Chris, the White Cliffs of Dover. This is really interesting geology for Europe generally, and for the geology of chalk even more broadly. And we're going to get into all that.
Hold on. No. It's the geology of the chalk. Okay.
The chalk. That's exactly right. Because let's turn to image number one here. This first image, this is the White Cliffs of Dover. These are an internationally famous landmark. Would that be fair to say? I mean,
yeah, absolutely. It's in every intro geology textbook. You got the White Cliffs of Dover for sure.
Oh, absolutely. And there's a reason. They're spectacular. I mean, these are beautiful. So these things, they're exposed around about 8 miles along the southern English coastline, and they're made up of this extremely white chalk. Julius Caesar wrote about these chalk cliffs in 55 BCE. The Romans installed some lighthouses along here. France is only 21 miles away. This is a very narrow point along the English Channel. And it's just this famous, beautiful exposure of rocks that has an exceptional geological story behind it. And Chris, I'll just flip to this next image because, again, it's extremely beautiful. This is spectacular. This is as beautiful as a seascape as you can kind of get, and just speaks to English geology, I think, to me.
I do. But what also, it is shockingly beautiful, but also it's geologically really important.
Yeah, very important.
This
geologically,
this particular...
historically, all sorts of interesting stuff tied up in this. You said it before. It's called the chalk. This particular chalk unit is called the chalk. So we're reading a paper called The Petrology of the Chalk, which is a great
we
title.
both thought that was funny. Yeah.
It's such a good title.
Well, the chalk, this formation formed during the late Cretaceous period, and we're talking about 100 to 66 million years ago. And actually, Jesse, this is interesting, and I think maybe a lot of our listeners know this, but maybe not. The Cretaceous, that time period, and it's marked by the extinction event. Many forms of life became extinct in a very short period of time, including the dinosaurs. But the root to Cretaceous is Creta, and that means chalk. So the time period, these were so abundant in every ocean that they named it an entire geologic period after these organisms.
It's very cool, Chris. And we're talking about you said the late Cretaceous. That's exactly right. So the entire Cretaceous period is 145 million years ago to about 66 million years ago. And so we're talking about the end of it. This 100 to 66 million year interval is the late Cretaceous. And I think that the origin of the naming and the subdivision of geological time is a really interesting topic. And it's frankly one that I don't know much about because I've spent most of my career studying the Archean, which is a huge time period with very few subdivisions in it, right?
That's right. That's right.
But things
I
like,
agree.
Yeah, sorry, go ahead.
No, I agree. I wish that I taught another class at the second or maybe a historical geology class at my high school. That would be fun because, just to take it to that next level, we can dive into things like this because I think the divisions in the geologic time scale they're really interesting, and like doing a dive into all of that. I think that's a class. That's a class cool. I want to take.
Chris, we can do it via the podcast. We should put this together for a podcast series here because it's famous. Creta means chalk, so therefore Cretaceous period is what we're talking about. There's things like the Jurassic is named after the Jura Mountains, and Switzerland and French border there. There are a lot in Pennsylvania, named for the Pennsylvanians. So there's a lot of these things in geology that go a long ways into explaining common themes in the geological record. And this is one of them. We're going to come back to this topic, but I just wanted to highlight this point you made. We're going to come back to this, that the Cretaceous, the end Cretaceous, is a particularly chalky period of time. And there's chalk exposed in a lot of places that formed during this time interval here. The chalk makes up the White Cliffs of Dover. And I'm going to skip ahead, Chris, to a very schematic geological map here. But this is mainland Europe down on the bottom right. And you can kind of see, France there. You can see the English Channel, and the black outline is the country. So you can see the UK here with England, Scotland, and you can see part of the other British Isles there. But the dark green on this diagram are places where the chalk is outcropping at the surface. And then the light green are places where the chalk is underneath of the surface, what we call subcrop. So the rocks are there, they haven't been eroded away, but they're beneath the surface. That's what subcrop means. And for the listener, basically there's two basins of interest here. There's a North Sea basin, which is to the east of the UK, northern England and Scotland, that North Sea there. So under there's a big basinal depression. And then there's something called the Paris Basin, which is on the mainland European continent, mostly around the Paris area in France. But it is, again, a basement. And you can kind of see this, Chris, especially in the Paris Basin. You can see that the chalk is exposed in a ring-like structure. And then it subcrops, it dives down into the earth in the center of that. So we can kind of tell just by looking at one unit that
it's buried beneath other rocks on top of it.
That's exactly right. And this is
which is typical with the basin. If you think about that, right? If you think about a basin, the central part of the basin is going to be, because it's depressed more, you get more deposition there. And on the edges of the basin is where it outcrops more often. I think of like Michigan geology. Let's jump back across into the US and it's the same kind of thing. And you have, that's right. And all these super old basement rocks, they're only exposed on like the perimeter of the Michigan basin, which extends actually beyond the state of Michigan, but same kind of thing going on here. Yep. It's this kind of bullseye pattern that you get.
And they'll be within the, those same rocks that are exposed on the outside will be present in the subsurface in the center of the basin. So the Michigan Basin,
for sure. Those they're there.
Rocks are exposed.
That's right. Yep.
Exactly. They're just down beneath our feet, which will become really important here briefly. But so, okay, we've had an episode on how do basins form, basically the formation of a basin. And we're kind of looking, there's this Paris Basin, there's this North Sea Basin, there's a few little smaller basins. And in between, on the margins of these basins, the chalk, capital T, capital C, the chalk is exposed. And it's particularly exposed in southern England, southeastern England, and then in mainland Europe across the English Channel there. And these exposures take place along this really cool uplift, not really an anticline, but it's an uplift feature that spans the English Channel. And so the chalk was laid down and then it was kind of uplifted in between these two basins and exposed more readily there at the surface. And there's a really cool geological story of how the English Channel formed with glacial outburst floods, etc. But these cliffs, they're really cliff-forming units, which is an interesting point, Chris, that chalk, we'll come back to the formation here, they are a cliff former in this region, in part because they're
why is that noteworthy to you? You know, we see that all the time. Chalk is a form of limestone, and we see limestone forming cliffs quite a bit. You know, we did a whole series on the Grand Canyon, and a lot of those cliff forming rocks are limestone, a flavor of, you know.
I think it's interesting, Chris, because of the region, the climate variability and what forms a cliff and what does not form a cliff. Like here in Pennsylvania, all of the valleys are limestone, shale or limestone, because it's easily dissolved. And I live in a karsty province in Pennsylvania where we have sandstone, shale, limestone, and we have those repeated back and forth and back and forth. The ridges in the Ridge and Valley are all sandstone.
The ridges are sandstone. The valleys are going to be shales and your limestones.
Shale or limestones, right? In limestone,
and that's because of your wet climate.
Yeah, exactly. Wet climate, more easy to dissolve. So we have to think of like weak rock, but also chemically weak rock.
Okay.
And limestone is a chemically weak rock, but in the Southwest, that you just mentioned, the Grand Canyon, out there's less chemical weathering, and so then limestone's really resistant, really tough limestone. And chalk
that's a good point.
So it ebbs and flows what's a cliff former and what's not a cliff former when we're talking about erosional
right
processes.
So that kind of leads into the next topic, I think, is that the chalk is a very important aquifer system in Europe. You know, I mean, and some of
this is interesting, Chris.
Yeah, it really
throw
is.
Some stats into this. This is super interesting.
Well, it supplies about half the groundwater for the public supply to England, about 1/5 to 1/4 for southern Belgium, about 10% to the public water system in France, about 10% in Denmark. I mean, so it's this really like laterally continuous layer that's providing groundwater, which is super interesting. Now, you know, in Michigan, I don't think of limestone as being a particularly like important aquifer, but you do in Pennsylvania. It's an important aquifer system, and it clearly is here too in this part of Europe.
So yeah, Chris, I mean, I'm trying to remember, what is the big western aquifer rock out in the western United States that picks up water in the Midwest, has some like glacial water in there still?
Yeah, sure. That's called the Lakota Formation, and it's got a lot of sandstone in it. It feeds the Ogallala Reservoir that runs under Nebraska and goes clear down to Texas. So super important. And I mean, you talk about extending the railroads west through Nebraska. That was very important because that formation is exposed in the Black Hills, which is this structural dome. So the rock layers, it creates these confined aquifers where it has impermeable layers above and below these sandstones. And they're tilted, which means you kind of have this water tower effect. You have pressure. And so they were able to drill down to that in Nebraska. They knew if it was laterally continuous far enough that they would hit that, and then it's under pressure. So it required less pumping to bring the water to the surface for the steam engines and all that. So yeah, super important. And that aquifer is really struggling right now. It's
is that
depleted.
Right? Okay.
Yeah.
So Chris, this links in nicely to the chalk, capital T, capital C, chalk as an aquifer system. It's massively important for huge swaths of Europe and UK. And so this has been the focus of a lot of study. I mean, entire volumes of journal articles, entire journals have been written on the aquifer system that is the chalk, or just generally chalk aquifers in Northern Europe. And it's a highly variable chalk system. And this is the reason why pulls together a bunch of threads we've talked about before. We've talked about karst systems and how limestone is easily dissolved, chemically dissolved. And so we get these fracture networks, we get little caverns, we get solution cavities, we get irregular flow, as opposed to a sandstone, which has a really regular, by comparison, flow network through the sand grains.
It doesn't have to create, sandstone doesn't have to create its own channels and avenues, whereas chalk and limestones do. They do this by solution.
Exactly, by solution. Yep. And so some of these chalks, Chris, exposed in the chalk, especially at the surface in England along some of these cliffs at the like surface exposures of the chalk, which this is a beautiful photo that you can see nicely. This horizontal layering, which we'll touch on in a little bit. There's horizontal layers in the chalk. This stuff, some of these rocks have 40% porosity, which is just a mind-blowing amount of porosity. That's like loose sand level of porosity. Like, pour sand in a bucket, how much water can you fit in there compared to the amount of sand you have in there? 40% of the rock is porous, but a lot of that
can I throw some stats on that a second, Jess, just real quick? Sorry to interrupt you, but if you think about let's say a bucket of well-sorted beach sand, I think of like Lake Michigan beach sand. You take a 5-gallon bucket or a 5-liter bucket, I don't care, and you fill it to the brim with that sand. What is the porosity of that? Well, you can measure that by just how much water can you pour in that's going to sit in the pore space and force the air out. And with that kind of sand, it approaches 50%.
That's a lot, right?
That is a lot, right?
Because what is actual sediment? You're describing really well-sorted, really kind of rounded sand grains, which is almost as much porosity as you can possibly get. I mean, it's not exactly, but as soon as you get a mixed sediment, the fine particles are going to fill in the gaps between the big particles. You're going to decrease the porosity. Here in the chalk, we're dealing with 40% in some instances at this surface exposed chalk. However, it doesn't drain very well. It's not very permeable. Those channels are not very connected. The flow paths are really irregular and difficult for reasons which we'll touch on later when we talk about how these things form. But link that process with a lot of room for water. Link that, especially at the surface water can get in there, and then link that with the way it can be dissolved, and you can get these solution cavities, you can get fractures, you can get fissures and voids. That means that water, when it can get through, gets through really quick. And we talked about this actually in central Pennsylvania. We've had this before. The groundwater systems are really robust and reliable, but they're really interconnected through these voids and fractures, which means the water is not filtering through. It has a short residence time. Water can travel really fast through these things, which makes them more susceptible to surface contamination, to pollution, and it means that you're not undergoing as many chemical reactions as you push water through these rocks. And so therefore it's kind of like more like a pipe rather than like a filter
right
system.
Exactly.
If that makes sense, right? Is that
it's like a sewer system kind of. Yeah, I think so, for sure. It's completely different. And the other thing is that a lot of this, you talked about how it's a cliff former, but it's not particularly what I would call stable. There are some really unstable areas within this. And actually, I think you can see this pretty well in this image, the instability of it down near the water, down near the ocean level there. Some recent large landslides, some mass wasting events have taken place. And so it's not particularly stable.
And Chris, that also has to do with the karstiness of this rock. This is a karsty rock. It can be dissolved. We can get karst, exokarst. It's a nice aquifer system, but it's a very variable aquifer system. So many of the regions where this aquifer serves, the water quality is deemed moderate to poor because it's really a carbonate hosted aquifer system, which is, again, doesn't do as much filter pressing, really, is a kind of a simple way to think about it. So
there are some other geologically interesting things within the chalk that upon close examination, you might be able to see things like some marl layers, which are these clay-rich layers that you get, which create these like impermeable perched water tables within the chalk layer. Those are, we think, maybe formed by volcanic eruptions that had a lot of like silicate minerals in it. And usually silicate minerals that are not quartz will, chemically weather into clay. And so that forms this clay-rich, what we call a marl layer.
So Chris, a marl is it's a very clay-rich layer typically. And when you're just describing the rock as a clay-rich layer, that's the term marl. If we know the origin, if we know, for instance, in some of these layers, you can kind of see some of the bands in this rock in this image here. You can see this horizontal banding here, darker colors. If we know its volcanic origin, then we call it a bentonite. Because we know, especially with volcanic ash fall, that stuff's really fine grained. And so it's really easy to turn that stuff to clay. I mean, many times it's often just volcanic glass, which has no internal crystal structure. So it weathers very quickly into clay minerals, and it forms these really, really, really easily expansive units. So the clay will shrink without water and it'll expand a lot with water. Out in the western United States, in dry regions, that's a big problem for buildings and foundations because it can actually expand so much it just compresses.
Well, we use this sometimes to pack wells.
Yes,
right?
That's exactly right. Exactly
so,
right.
you drill a well and you want this to be kind of like airtight, pressure-tight system. So we'll pack the well in this bentonite. When it gets wet, it kind of just seals the whole system up. So, Jesse, one other thing that you can see in this, lenses of marl, but you also get lenses of chert, which is this just really it's a form of quartz. It's this silica-rich, these lenses that occur within this.
One of Chris Boyce's favorite rocks, if I dare hazard a guess. Chris is a chert man.
How can you not be, Jesse? Honestly,
I mean, I agree. It's it's a good one. It's a really good one. But how do you envision? I mean, what's your mental model for how chert forms?
Well,
apart from a lot of different ways.
I mean, a lot of different ways. It's a microcrystalline flavor of quartz, and it forms diagenetically, which we're going to get to. Are we coming up to that right now, Jesse? Are we moving in that direction? The diagenesis of... Okay, well then...
Of this process. Well, maybe before we get to that, because you're right, silica, so these silica bands, these chert bands, can form during diagenesis for sure. There's some other variety of ways you can get nodular chert in the chalk layer, in the chalk unit. You can get several different varieties of these. You can get flints, you can get stylolites as well, which are a different feature in here.
And it can be quite colorful too. It's
it can be really pretty. And there's a whole bunch of, basically you got to think of this as a sedimentary rock unit that is laid down progressively over time. And there are time changes throughout this. From the bottom to the top, things change. There's different categories. There's the gray chalk, the white chalk series. They've been subdivided to death. We're not going to get into all the details of all the subdivisions here, but there's a wide variety of different chert styles in here in different layers. These are really good index layers that sometimes are really horizontally expansive. So they can be mapped across huge swaths of the chalk outcrop, both in outcrop and in subcrop as well. So,
well, before we get into that part, Jesse, let's talk about the Cretaceous. What was the world like at this time? Because this was a very different looking world than what we have today.
It was chalky, Chris, right? The name tells us it was chalky.
There you go. That's right. That's right. But it's true. I mean, there was like chalk was forming everywhere. It was very, very prolific. So what was it like during the Cretaceous? To be really general, it was much warmer than it is today. I mean,
much warmer.
So in other words, we're talking about forests that went from the equator all the way to the poles. Now, there were times where there were probably glaciation, but these would have been glaciers that stuck to the poles during certain times and would have maybe sprawled to lower latitudes, but they never extended very far during this time period. So,
Chris, it's really important to think about what the relationship between glaciers, climate, and chalk deposition, especially chalk deposition in the areas that we're going to talk about chalk being deposited, because the sea life changes dramatically when you do this. So think of all of the ice that we have tied up in the ice caps, the Antarctic ice cap, the Greenland ice cap, Arctic sea ice.
About 10% of the land continental surface is covered in ice today. And
that's
a lot
right.
of it.
And so that's a huge amount of water tied up in ice. And so you melt that and you raise sea level. And you raise sea level enough to basically flood the continents. And I always like to use this visual. Where I live in Pennsylvania, it's kind of an easy visual, and I think where the chalk is exposed is a pretty easy visual. You don't need to raise sea level very much to flood all of the United Kingdom, much of mainland Europe. The same thing goes for here in Pennsylvania.
Yeah, the East Coast and the Gulf Coast are just destroyed.
It's really flat. Like we have this whole Piedmont province that's like a couple hundred meters, not even, several tens to 100 meters above sea level. As soon as we get into Pennsylvania here, sure, you got some ridge and valley province, but like you could easily flood this with a couple hundred, maybe 500 meters of sea level rise. And so it's kind of this tipping point where the continents, the low-lying parts of continents, which we talked about the hypsometric curve, there's a very limited amount of Earth's surface area that is high mountain ranges. It's a pretty small part, and there's a huge amount that is flat-lying continents kind of roundabout near sea level. And so if you melt all the glaciers rather, and dump all that water in the ocean, it's going to raise sea level and it floods the continents. And what happens, it sounds okay. It sounds like interesting. Let's just flood the continents. Okay, easy. But actually think about what happens. If you flood the continents, what's life going to do? What are those oceans going to look like? The climate's going to be warmer. So the ocean water is going to be warmer.
Teeming
And all
with
of a sudden,
life. Yeah.
yes, we have relatively shallow seas that are huge areas. I mean, you could imagine this being a really rich ocean life environment because
sure.
it's all
And
really shallow.
Yeah, and it's we're talking about warm water. It's very shallow water, so photosynthesis is just booming. That's the scene during especially the late Cretaceous. That's what the world was like.
We're talking about tens of, if not hundreds of millions of years at this level. So this is like just a very different planet. This is a very different planetary starting point for life. Like, as we've talked about before, all biology does is respond to the geology.
Of course.
For the most part. It's not quite true.
Jesse, something came across my feed the other day. Somebody is starting to offer a degree in geobiology.
Okay. Well,
I don't
we have
know
a
who,
geobiology
but
degree. Penn
Do you
State
really?
has one. Yeah, it was a
Are you
geobiology
serious?
degree program. Yeah. We've got several geobiologists on our staff, and it was a big push like a couple years ago. Yeah. And
what's the
I don't know too
breakdown?
much.
Is it like in terms of how much geology and or is it just all blended together?
It's a really tough thing. So okay, well, we're getting into the weeds here of our program, but our program has a limited number of hard requirements. Even for a geoscience degree, there's like 6 or maybe it's 8 classes that are required, and then the rest are kind of just take whatever you want in the 300 or 400 level, whatever's offered at that time period. So it's kind of mix and match even to begin with. I don't know exactly what the geobio degree program, what the requirement breakdown is, but I will look into it and report back to you.
All right.
Because yes,
Well,
I mean, I don't know if it satisfies anybody, but Chris, this time period we're talking about, what's called the Cretaceous thermal maximum, and the peak temperature here was about 90 million years ago. So right smack dab in the middle of this late Cretaceous period where we're talking about the chalk being deposited. And, we're dealing with a big rise in CO2, high CO2, really a warm environment melting all of the glaciers. So that's kind of the idea here.
So Jesse, I think that's a good time and a good segue to transition into what is chalk, like a little bit of the biology combined with what was going on with the atmosphere. And like you said, carbon dioxide dissolving into the ocean. So chalk, these are microscopic organisms. Basically, these are single-celled algae. And so, like, when you think about that and you think about how fine-grained the chalk is, that's what we're dealing with. You think about, look at the White Cliffs of Dover, this image that we have in front of you right now. Hundreds of feet thick, but these are mats of microscopic organisms. And that's a crazy thing to kind of try to wrap your mind around for a second. So these were photosynthetic, single-celled organisms that were producing these calcareous plates. They're called coccoliths.
Oh, here we go. Hold on, Chris. We got an image for that. Here we go. Skipping forward. Beautiful. I mean, these are SEM images of individual organisms, really.
Let me back up a second. The organisms themselves are called coccolithophores, which is they're a flavor of foraminifera, or what we call commonly forams, right? But they made these. Look at these plates that they're making. They are very, very cool. So they're making these calcareous plates, and when they die, they just settle down and accumulate on the sea floor, and that's what the White Cliffs of Dover, or all the other chalk formations that outcrop, throughout the whole world, basically. We've got a lot of it in the U.S. as well. That's what it's made of. And that's a crazy thought, because these are single-celled, microscopic marine organisms. Super, super important, though.
I agree. It's a extremely important and really cool story. So the depositional rates here are not you would think, oh, this is extremely low, but it's not actually that low. They're not a crazy slow depositional process because the ocean is teeming with life. There's so much of this biological activity going on, again, because ocean water is warmer, the continents are flooded. All of this stuff is happening to keep the depositional rate from being like crazy low, basically. So this is a really productive time for these shallow ocean shelf areas. And so, Chris, should we come back to home turf and highlight a couple examples of other important geographical examples of chalk?
Let's do that. But before we do, I want to just say, because we did talk about it, the extinction event, the KT event.
Oh yeah. Yeah, absolutely.
Many of the foraminifera became extinct after this, and chalk did not. They suffered greatly due to this event that happened, but they're still around today. And that's amazing to me as well, that these same organisms, and there are many, many different species of these coccolithophores, but they're still around. That's pretty awesome. They made it. Which is that's what happened, right? During this KT event, most of the bigger ones died off, much, much less diversity, but these, because they were so small, they made it. So,
yeah. And it's not a huge difference it's a big difference in the life forms, but the temperature differences, we're talking about 5 to 7 degrees, ocean chemistry, something like that. But it just makes that knob can get turned up really quickly to rapid, especially when you flood the continents, lots of deposition or lots of life happening. And then the end Cretaceous, as you said, extinction event happens and it's a hard reset, basically. So, Chris, a couple other examples of chalk, really, that are kind of famous. We talked about the White Cliffs of Dover. That's the chalk, capital T, capital C, extends all over the Paris Basin. So there's huge chalk cliffs as well as you get off into France and the northern European basin. We showed that image before, including parts of Germany, Denmark, and the Netherlands even. So this is a very expansive unit across most of Europe. We also have, Chris, here's a photo of I think I'm pronouncing this right, Niobrara formation. I don't know. Do you know how to pronounce this particular one?
I primarily I know it's a formation, but I refer to the pure shale, which is a whole sequence of rocks.
And this is how I usually a formation within the pure shale. Yeah. So this is one that is very common in the Western United States, which again was a flooded continental shelf at the same time period, deposited
an interior
chalk.
seaway, and
exactly. And here we had several examples of these interior seaways, but we had a Cretaceous example. And Chris, this is interesting to me. This is a photo from Kansas, so there actually is some topography in Kansas. It turns out it's not just flat. If you would ask me before, I've driven across Kansas a couple times, and man, can it get flat? No offense to the Kansas people,
I'm not gonna go there. I'll rip on Nebraska all day long, but I'm not gonna offend anybody from Kansas
You'll
today.
rip on Nebraska all day long, but Kansas is off limits to you.
Yeah, Kansas is off limits. That's right. That's right.
Funny. Why is Kansas off limits, but Nebraska's fair game for you?
I don't know. I just feel like if you find yourself living in Nebraska, I think you've made a poor life decision somewhere along the way. I don't know. Please don't send me hate mail, but it just doesn't do it for me. You're driving and you're driving. It's a big state, and many times I've driven through Nebraska
You're completely biased because you're driving. That's like for you leaving from Michigan at 5 a.m. You leave from Michigan on the big yellow school bus and you head out west. Nebraska's where it gets starts to get painful length of drive, and then it doesn't help
just
that
a lot
it's
of corn.
pretty flat. Yeah, and then you're also like looking forward to the mountains by that point too, and you're like, we just need to get to the mountains. So. Eastern Colorado has some of the same vibes sometimes, but
you got that right.
It's just because you're at the end of a long drive. That's all. So
okay, all right. So I take it back. I'm sorry, Nebraska. You're
take
okay.
it back just a little bit.
I take it back.
yeah.
But all right. So Jesse, let's get into the geologic setting for the formation of chalk. Okay, what do we got to have? I like this. This is like organization. Mentally, my mind needs this. Your mind is more scattered than mine. But what do we got to have? We need shallow warm seas. Okay. And we've established that. That's what the Cretaceous was like, especially the late Cretaceous. So continental shelves are submerged. We need warm, shallow water, ideal for photosynthesis. What else do we need? We need the water to be relatively calm conditions. So these are low energy environments. So because what happens then? They're just allowed to settle out undisturbed. You don't have this, it's not very turbulent and things like this.
Extremely
and so you
important,
get this,
right?
Yeah, it is. It is
to get
extremely
a finely, and you look at this photo here. I mean, you get these really fine laminations. I mean, I've seen this stuff, Chris, when I was an undergrad. We went and drilled some of the post-glacial, post-dune lakes sitting behind, well, in the west side of Michigan. We have these dunes along Lake Michigan, and there's great lakes sitting right behind them. And they're really calm because all the storms come. The storms get kicked up over the dunes and don't really impact these lakes. And so you have really fine laminations in the sediment preserved. They're really small, really calm. So you get these tiny laminations that are preserved across it. And the same thing is going on at a continental scale in some of these. I mean, you can chase individual chert layers that are a couple inches thick
laterally
for miles
continuous.
and miles and
Yeah, that's
miles.
right.
That only happens if it's a really calm, really homogeneous environment across most of that area.
And the other thing really that you touched upon already is you have very slow depositional rates. I mean, we're talking fractions of a millimeter per year. So these are really, really slow rates. And they're usually deposited in how shallow is the water? On the scale of a couple to a few hundreds of meters deep. So not very deep. This is like really broad, flat, submerged continental shelf areas where this is happening.
And Chris, the other thing that's interesting to think about here is, okay, this is fractions of a millimeter per year. That's on the slow end of normal sediments, but it's in a normal sedimentary depositional range. It's not chemical deposition, let's put it that way. It's not, we were talking about the manganese nodules on the sea floor that are doing millimeters in millions of years. I mean, really incredibly slow stuff. So this is much faster than anything you'd see in the deep, deep, deep ocean today. That's incredibly slow deposition. This is
that's right.
Slow on the scale of sediments that occur on continental shelves. But you have to think, if we flood the continents, again, I want to kind of paint this visual. If we flood the continents, there's a lot of activity that happens in a modern continental shelf environment. We have these submarine landslides that take out some of the transmission cables and the fiber optic cables that go across the Atlantic. When you're on the edges of the continental shelf, that's a very dynamic underwater environment where you're getting deposition, you're getting sediment going out, you're getting clastic sediment going out into the ocean. So it's really dynamic. If you flood the continents, then you have this huge expanse where there's not much relief on the ocean bottom anymore. Whereas like our modern continental shelves, there's actually a decent amount of relief. There's a big slope drop off there. Flood the continents and that still happens, but you have this big expanse of, like you said, couple 100-meter deep ocean water. So there's a lot of room to have really calm water. And the ocean currents are going to be totally different because you have this like really shallow continental part of the ocean and then the deep normal ocean basin. Whereas now really only have the deep ocean basin.
You touched on something that I think is worth noting. Why are the sediment accumulation rates so slow in the deep ocean? A lot of different reasons for that, but the deep ocean, you're not going to get sediment that is land derived, what we call terrigenous sediment, that's going to make its way that far off into the deep ocean basin. It's going to be deposited before it gets to that point. And then you talk about like maybe this kind of sediment accumulation, like this kind of bioclastic stuff. Well, even that's not going to accumulate in the deep ocean waters very much because limestone, calcium carbonate, you have to saturate the entire column of water in order for that to happen. So even if these things are living in the shallow water.
Let me just jump in there. What do you mean by that? You mean that, okay, so in the upper part where the organisms live, they build their shells out of calcium carbonate, but you need to have that calcium carbonate skeleton, their house, after they've died, it needs to sink down and it needs to not be redissolved by the water column, which means you have to have enough calcium carbonate, bicarbonate in the water so that it doesn't redissolve it. It's either precipitating or redissolving. It's not doing nothing. And so you have to have it, and that's what you mean by saturate the entire water column. So we get down in the deep ocean, you get down to a depth that stuff is dissolved again.
Yeah, because the entire column of water, 3 miles deep or so, whatever you want to do, it's really, really deep water. is not entirely saturated in calcium carbonate. And the other thing that's happening too is that calcium carbonate is a little weird. It gets more soluble in cold water, which is not normal for when you think of like dissolving salts or sugars in water, and you heat the water up and you make it becomes more soluble. Limestone is the opposite of that. So deep oceans, colder water, that also favors the redissolving of these dead coccolithophores. So anyway, that's just a side note, but yeah.
So these things get deposited, and we've talked about this, the slow deposition, calm conditions, warm, shallow water, the late Cretaceous thermal maximum here, very different world than what we think of today. Now we have to make a rock out of that. So we talk about diagenesis now. Now that's the term, diagenesis. We're forming a rock out of this sediment. This loose sediment is going to get compacted, cemented together. Those are the two processes to turn sediment into rock. That's the next step. And so it's really kind of simple to think about, but there are some dramatic things that can happen during this process, including forming some of these chert layers during this process, diagenesis. And we think of diagenesis happening in the many meters to deeper beneath the subsurface. And so I think it's important to kind of think of how this is going to change the chemistry here a minute, because so compaction is kind of simple. You put more sediment on top and the stuff beneath it gets squished and squeezed, and that can squeeze out the water that's trapped in there. But you're getting ocean water kind of trapped in the sediment as it's getting deposited. But that water is also kind of flowing around and communicating with the surface water at some level. But there's a gradient, a chemical gradient from the top to the bottom. So deep down in the layer, still loose sediment, you can get chemistry, water chemistry, that's very different. Like all the oxygen could be gone out of it because let's say there's some organic matter being deposited along with it. That stuff's going to decompose, soak up all the oxygen out of the water, down the pore water now that's trapped in the loose sediment, and it's going to take that water and remove all the oxygen from it. And that's one of the processes that could dissolve and then reprecipitate silica-rich bands. So these silica-rich bands, or these chert layers, some of them are certainly just silica being deposited as the sediment's undergoing diagenesis, really. It's part of the diagenesis process that there's fluid kind of moving through that is silica saturated, and then it hits a gradient, a chemical gradient, and starts to dump out, precipitate that silica into a chert layer or chert nodules.
I have a question for you. Do you call this in your class, your intro level classes anyway, do you refer to this process as diagenesis, or do you just call it lithification?
I talk about diagenesis as the term. For no actual real good reason, I guess, now that I think about it. But yeah, I talk about it as diagenesis and compaction, cementation. We got to cement the stuff together. How about you?
I usually refer to it as lithification. Just, but same thing. It's a two-step process. Yeah. Turning sediment into rock, basically, is what we're talking about. And it gets complicated, especially in the deep oceans. Anyway. The chemical reactions that can occur during diagenesis are incredibly important, and they get really complicated really quickly. But they can do a couple things that we can see in the chalk and another chalk around the world. That's right.
So
that's right.
Yeah.
Well, Jesse, we're about ready to wrap up our riveting discussion about chalk.
Oh man.
But I think I think we've talked about what chalk is. We've talked about the geologic setting of the time period where these were so prolific. We've talked about the diagenetic processes. Now let's talk about, why is chalk important? Is there an economic significance and importance to chalk?
So I think most people have probably heard of chalk or even used chalk as like chalkboard chalk, right? Stuff you use on the chalkboard. And they would assume maybe that's coming from the chalk layer, which historically would not be wrong, right? I use chalkboard chalk. I still use markers more, but many of our classrooms have the old chalkboards in them.
No way,
still.
Really?
Tons of our classrooms.
Crazy.
Yeah.
I would think only the physics department would have chalk. Only the physics department.
Chris, the one I lecture in, I mostly use PowerPoints. Every once in a while I'll go to the chalkboard, but it has those ones where there's like 3 chalkboards.
Oh yeah. You're sliding them all over.
Well, you slide them up, so there's actually a 3x3 grid of chalkboard. So there's 3 horizontal, and then you can slide them all up. So you can write on it, slide it up, write on it, slide it up.
I'm
totally
old.
cool. I mean, a huge lecture hall full. Anyway,
Well, hold on. It's hard. The numbers on chalk are difficult, right? Because
I couldn't. We struggled to find hard and fast numbers to put on chalk mining and chalk extraction, it is often lumped in with aggregates. And
the
so
other flavors
that
of limestone,
includes-
right? Yeah.
or even just like sand and gravel and crushed aggregates, like, stuff that's going on roads, which is not necessarily chalk, right? So there's very few, even U.S. Geological Survey reports that tease out chalk as separate from limestone quarrying and limestone uses. But it's safe to say that in countries where chalk is mined regularly, for instance, like France or the UK has relatively, I wouldn't say prolific, but the chalk quarries are around. It's on the order of tens of millions per year, US dollars, at the least, in recent years. But it's hard to put really hard and fast numbers on the economic importance of chalk in the modern era. Chalkboard chalk used to be real chalk rocks, but now is more what they call mineral chalk. So it's like crushed gypsum. It's manufactured gypsum.
It's so
or other
disappointing.
minerals.
Yeah.
I know it is. You know what would be a good here? Okay, here's the thing, Chris. Do you use a chalkboard do you have a chalkboard in your classroom?
No more. Nope, I don't.
Oh. Okay,
Nope.
well, you get a chalkboard, and if there's a listener out there, especially from the UK, who wants to send us a nice gift, give us some chalk pieces from the chalk that I could use in my classroom. That'd be kind of nice. I'd love to teach with chalk from the chalk. That'd be pretty good.
That's a really good point.
Excellent.
That's a good point.
Etsy must somebody on Etsy must make these, Chris, don't you think?
I would. You would
look
think,
into
right?
this.
You would think somebody's got to do. So, all right, let's move on.
I'm focused on this. I want
I know
this
you are.
now. We got to find this out. I want to get this. All right, sorry.
Well, you go to the
other
UK
uses of
quite
chalk.
often. You do your doctorate presentations over in the UK. So you're gonna have to make this happen.
Maybe I'll go
do
give
it
a talk
yourself.
at Oxford, and they'll give me a
Yeah.
piece of chalk from the chalk.
Yeah,
That'd be good.
that's right.
Yeah. Anyway.
Another thing is like cement production, mortar, concrete, things like this, plaster. They use chalk as this kind of binding agent in it, and this is something too. I've worked with this extensively actually when I made my my beautiful rock pillars that line my driveway.
Oh yeah.
Because when you clean it, you use muriatic acid or hydrochloric acid, and you get that reaction with the lime, the calcium carbonate that's in the binding agent holding the mortar together. So
that's the Portland cement.
Yep,
Yeah,
for sure.
Okay, yeah.
Yep.
So you can see it. You don't see it fizz, do you?
Oh yeah, absolutely. Fizz is like crazy. Yeah.
Oh, interesting.
Yeah.
Gotta be careful. Dissolve away your nice columns there, Chris. You gotta be careful.
Oh no. But it does it's havoc on your hands. Like seriously, it's.
Oh yeah. Well, I mean, you probably won't be wearing leather gloves. There,
I know, but sometimes you just
gloves.
can't. You just can't.
Oh,
sometimes
you just health be damned. Don't follow Chris's health and safety advice.
Generally, that's bad advice anyway. So yeah.
Yeah. This is definitely true. Soil treatments, lime, ground chalk is used for this. Any kind of calcium carbonate can be used for this, and it can be used as a livestock feed additive. So
I got to do this. I have to do this in my own yard. I have a pine tree that is making my soil very low pH, too acidic, so I got to add some lime to it. Yeah, I can't get grass to grow in a certain spot. Yeah.
Dump it around there. Okay. I'm sure the pine tree is super happy about that you dumping lime on its roots, but
I'm on it.
Whatever.
I'm on it.
You're on it.
Got to do what you got to do. That's right.
Got to get the grass going. So there's a whole host of these. Toothpaste often has chalk in it as an abrasive. And that's interesting, right? Because you imagine, I'm going to go back to this image. Imagine these little guys, these little fossils, they're pretty abrasive, right? There's a lot of sharp edges on this stuff, right? So it's a really good abrasive, no real health effects when you eat calcium carbonate like this. So it's a good thing to use. Antacids have this. And in the coming energy landscape, carbon sequestration, chalk has been highlighted as a potential use for carbon sequestration mechanisms as well, too. So lots of potential uses and lots of very active uses for chalk.
Yeah. We use it for antacids. I've used it personally for antacids many times out in the field.
Never from the chalk, though, just from other
chalk,
lower grade chalks.
But we use it as a filler in paint and also in paper manufacturing. It makes paper smooth, which is kind of cool.
Okay, there we go. The great many uses of chalk.
Yeah, just some uses. There we go. Yeah.
You know what, Chris? It's a beautiful rock, chalk, and it makes some beautiful terrain. The White Cliffs of Dover, it's a really cool geological story. We can talk maybe another episode about how the cliffs themselves actually formed and what cut the English Channel and all that kind of stuff. Very exciting geological stories to tell over there, far across the pond. But
yeah,
White Cliffs of Dover,
you know what? Who would have thought the importance geologically and economically, and it's an interesting story. Chalk has a story to tell.
Very interesting story. Yep, absolutely. And you know what? There's historical stuff to tell here as well. I mean, it's just a very striking feature of the landscape in southern England there, across the English Channel. Hey, that's the story of Chalk. What do you think, Chris? Good? We done? Wrap?
I think that's a wrap.
Here?
Yep,
all
wrapped.
Right. Hey, you can find us on all social medias. We're at PlanetGeocasts. Go to our website, planetgeocast.com. Shoot us an email. There's a contact us link there at our website. We love hearing from you. If you're listening on YouTube or Spotify, please subscribe. Leave us a like, review, and a comment. We always love hearing that.
Cheers.
Peace.